Hello, my name is Aaryan Chatterjee, and this is my Circuits Lab 3 in Physics 2212. In real life, circuits will be described as a complete pathways where electricity can flow through. This lab will focus on predicting and analyzing how certain circuits will act and what properties they will have. More specifically, the purpose of this lab is to analyze a circuit and its properties with resistors, capacitors, and light bulbs. We'll predict the values of the current and voltage with mathematical equations, but we will have a real circuit where you can measure the actual values with a multimeter. Later, we'll see that the written analysis and the actual circuit provide extremely similar results for circuit properties, with the current being 0 to 0.02 amps and the voltage being 3 volts, and this is for the part 1 circuit. But before we jump straight into the lab specifics, I think it's important to understand some of the crucial physics principles and ideas utilized in this lab. Firstly, it's important that everyone understands the loop law, which says that the change in electric potential of the entire circuit must be zero due to energy conservation. Then the node rule says that the current flowing into the node must equal the current flowing out of the node due to charge conservation. Then Ohm's law connects voltage, current, and resistance with the equation V equals IR, which allows us to solve for any of those variables. Finally, a resistor is a circuit component that regulates the flow of current, while a capacitor is a circuit component that stores electric charge and also affects the circuit's current. Now we discover some major assumptions in the experiment, and one is that there are no external factors that are affecting the circuit and its properties. Additionally, everything in the circuit is assumed to be properly connected. On top of the assumptions, it's important to note that the system which what we will analyze is the entire circuit in the experiment, and everything else is the surroundings like the ground. This picture is what the first circuit will look like, and the current will flow from the positive end of the battery upwards. Additionally, the voltage of the circuit is 3 volts, indicating that each battery is 1.5 volts. Now, moving on to the circuit predictions, we know that the voltage is 3 volts for the circuit, and there's a total of 147 ohms of resistance in the circuit. Thus, using Ohm's law, we can solve for the current and find that the current should be around 0.02 amps. And additionally, using the node rule, you can see that I1 and I2 must equal each other, meaning that both of the currents are 0.02 amps. In order to check that we predicted the right value, we then built the circuit, which is shown in the right picture, and we calculated the current at both I1 and I2, and found the current was indeed 0.02 amps, indicating that prediction was right. And just as a side note, since the pictures of our built circuit is very messy and hard to understand, I'm going to use pictures from an online circuit from now on, but the data is still from the actual circuit. Then, to further analyze the circuit, we replace one of the ammeters with a voltmeter and find that the voltage is 3 volts, which is to be expected at the location measured. Additionally, we see that the current is 0 amps, which is shown by the ammeter, since the voltmeter essentially stops the current of the circuit. Moving on to calculate the potential differences throughout the circuit, it's important to factor in the loop law, meaning that the individual potentials of the circuit should add to 0. Additionally, potential differences would be non-zero only if there's something that affects the circuit between the 2 points we are looking at, so a lot of potential differences here are 0 and they're written down. However, the potential differences that aren't 0 are the ones on the battery and the resistors. So as you can see from the picture on the left, the voltages of the battery is 3 volts, the voltage of the 47 ohm resistor is negative 0.94 volts, and the voltage of the 100 ohm resistor is around negative 2.06 volts, which is correct since they add up to 0 volts, satisfying the loop law. And this is the voltage graph for the circuit, and as you can see, it first goes up from the batteries to 3 volts, and then it goes down a bit from the 47 ohm resistor, then it goes completely down from the 100 ohm resistor and back into the batteries, completing the circuit loop. Finally, if you make a parallel path that goes around the 100 ohm resistor, the current goes up from 0.02 to 0.06, since the circuit effectively goes around the 100 ohm resistor, resulting in there only being 47 ohms of resistance in the circuit. Additionally, when we calculate the resistance of all the circuit components, which can be seen in the picture on the right, we tend to be a little bit off the correct values, indicating that there could be some errors, like rounding. Moving into the RC circuit, which is the circuit with the resistor, battery, and a capacitor, we will build 2 circuits where there's a 10 ohm light bulb and a 20 ohm light bulb. However, both circuits will have a 9 volt battery and a 200 microfarad capacitor. For our circuit predictions, I predict that both light bulbs will shine brightly at first, then they will start to continually dim as the capacitor charges, and once the capacitor is fully charged, the light bulbs will turn off. However, the 20 ohm bulb circuit should take longer to charge the capacitor and discharge the capacitor, since it has a higher resistance, meaning the bulb will stay on for longer. Moving on to the actual data, the RC circuit with the 10 ohm bulb had a 7.5 second charging time and a 9.4 second discharging time, and the RC circuit with a 20 ohm bulb had a 18.4 charging time and a 19.3 discharge time. Additionally, my prediction was completely right as both bulbs turned on and diminished over time, but the 20 ohm bulb stayed on for longer since the high resistance made the voltage move slower to get to the capacitor. Finally, I took a potential difference measurements in an RC circuit with a 9 volt battery, 200 microfarad capacitor, and a 30 ohm light bulb. And using the data I got, I found this linear equation representing the potential difference as a function of time, and this is what the graph should look like. From the line equation, we were able to find the RC of the circuit, which is negative 1 over the slope, which gave us 6.83 seconds. Additionally, our prediction RC was around 6 seconds, so that means our predictions were very close. Some source of error in this lab is that the external forces and fields could have affected the build circuit, giving me slightly wrong values. Moreover, there could have been a mismeasurement or rounding errors, resulting in differences of predicted and real values, and there could have been a human error by me setting up the circuit with loose connections affecting our data. For our what if question, if there is a battery in a capacitor with no resistance, in an ideal world, the capacitor would instantly be fully charged. However, in reality, the wires and batteries would have some resistance, meaning the capacitor wouldn't be instantly fully charged, but would take some time. And that's all for my presentation. Thank you for listening.